welcome back to this course on computational thermodynamics and kinetics of materials. Today we will continue with more hands-on sessions on kinetics. These are going to be the contents. First we will see some basics of this oral transformation kinetics, how it is tracked in an isothermal transformation, and then we will do a hands-on kinetic simulation of that transformation. Then we will see TTT diagram and CCT diagram, what are they, and then simulate TTT diagram. Okay, let's see what is this isothermal transformation, overall kinetics of it. What we are going to do is take samples of the same alloy, multiple samples of same composition, and keep them at one particular temperature so that some parent phase is there stable. Right, from there we take it to another temperature where this parent phase is metastable and product phase will form. And this product phase, it may be one phase or multiple phases, doesn't matter. This product phase at different intervals is checked. So we take out the sample after different times and figure out what is the fraction of product formed. Then plotting this product formed fraction versus time will give us an idea of overall transformation kinetics. So this is what we are going to do, multiple samples of same alloy at isothermal exposure. Then products nucleate and grow, samples taken out at different intervals. The amount of product formed is characterized. So we figure out what is the volume fraction of the product formed with respect to time. Then this is plotted, fraction of product formed versus time. It's going to look like this, fraction of product against time. It will have usually this sort of shape where initially there will be something called an incubation period. This is an incubation period, meaning the transformation has not significantly started. And beyond certain time, it starts and it goes like this and then gradually ends. So this is how the transformation happens. This incubation period is there because of a couple of reasons. One is due to low driving force for nucleation. This can happen. You can understand why it happens because at small undercoolings, we know the driving force is going to be less. The delta G bulk is going to be less. You know what we are talking about. We are talking about this. If we go for a smaller undercooling from Tm to this temperature, we get a small delta G. A higher or a lower temperature will give even higher delta G. So at small undercooling, somewhere near this melting point if we go, undercooling is too small for the transformation to start significantly. Therefore, nucleation rate will be very less and the incubation period will be large. Okay. Also, due to sluggish diffusion, where especially at large undercooling. So if we think that if we go for a very low undercooling, delta G will be really high, therefore more nucleation can happen and transformation will be fast. But it will not be so. If you remember that capital D, the movement of atoms in the parent and in the product, especially across the interface, these diffusivities are going to matter and they are going to be very less if you go to very low temperature. So there should be some sweet spot undercooling, that is where the nucleation rate, growth rate and all will be optimal. So this graph gives you an idea of what is the incubation period at different temperatures and how the transformation happens with respect to time when it is getting completed. All this information you can know from overall transformation kinetic graph of this sort. Okay. Let's simulate this taking an example. Fraction of product versus temperature plot will go. This example P04 in thermocalc is already there, worked out example, saved as a project file. You can simply run this and understand this. And precipitation module is a separate module in the graphical user mode. We have used diffusion module, we have not used precipitation module. If we use this, all this overall transformation kinetics will come into picture. Then in this particular alloy, iron carbon alloy with carbon 0.016 mass percent, very less carbon. This is the alloy, so overall composition is here. This is the 0.016 mass percent. So this is the iron carbon phase diagram at this extreme left end. The maximum carbon itself is 0.05 and up to 1000 degrees it is plotted, 1000 degrees Celsius. And the transformation is going to be precipitation of cementite from BCC. How is this? You take BCC, single phase BCC in this alloy, it is possible at this temperature. Make it and then bring it from that furnace to this furnace. Okay. So multiple samples of the same composition are kept at this 102 degrees for a long time. and at different intervals samples are taken out and characterized. How is the fraction of cementite formed? You know, if we want to figure out the equilibrium phase fraction of cementite, you can have a tie line here and apply the lever rule and figure out the maximum cementite or equilibrium amount of cementite that can form. So that will be the completion of transformation. So we will see overall transformation kinetics by getting fraction of product versus temperature plot and keep other parameters with default values. Let's see how to do that. As I told, this precipitation demo, this P, this is the module that we need to use to do this particular example. But I will not go to this module and set up the calculation ourselves. I am going to run an example file that is already there. I go here, this example files, click on that. Here you can see precipitation module, the old name is TC Prisma. So this one we are going to use now, precipitation module, double clicking on that, and P04 precipitation FEC cementite. This is the example that I am going to run. So click on it and open. Okay. It takes few seconds for it to populate all the different parts of the tree. Wait for that. Okay, so now it is over. It is back to this initial stage. This is when it is over. You can see multiple stages are there. The system definer, I will show you. You can see both the databases, thermodynamic and mobility databases are selected, and two elements, iron and carbon, are selected. Alright, and in the precipitation calculator, you can see composition in mass percent is 0.016 for carbon, and then there are these two different phases. One is the matrix phase, which is BCC, and precipitate phase. The product phase is called as precipitate phase in this precipitation calculator, and the parent phase BCC will be there. Inside that, cementite will form and grow. Okay, and here nucleation sites are given as dislocations. So this is based on experience that the preferred nucleation sites, the heterogeneous nucleation sites in this cementite formation are dislocations, and certain aspects, interfacial energy aspects, all these things are experimentally available, and that data is used here directly. Okay, and then isothermal exposure is selected in the calculation type at 102 Celsius, and the time, simulation time, is 6 lakh seconds. This is what we are going to simulate. So we will see how the phase fraction changes with time. You can click on this perform isothermal simulation. Okay. It takes quite a bit of time to complete the simulation. Once it is over, you get this plot here. Okay. You can see here volume fraction against time. You see this sort of graph here. Okay. The blue line is from the simulation, and the triangles which are there superimposed on that are the experimental data. You can see here experimental file reader. In this, the experimental data is fed, and that data is made as a predecessor to this graph. So therefore you get this volume fraction data versus time superimposed with the experimental volume fraction versus time. So there is a very good matching between the experiments and simulation. So this is isothermal transformation, overall transformation kinetics. You can see what is the incubation period, you can see what is the time, you can see the time at which the transformation starts and the time at which it ends. So these are very important information for any industry practice. Now let's understand what is a TTT diagram, time temperature transformation diagram. You see the fraction of product versus time graph is here for two different temperatures, T1 and T2. Okay, and the transformation start point is here, transformation end point is here. Okay, similarly start point is here, end point is here. These points are taken to this graph of temperature versus time. Okay, so in the temperature versus time graph, we are going to give the start point of the transformation and the end point of the transformation against that particular temperature. So T2, this is the start point and end point. So go to this T2, this is the start point and end point, mark it there. Similarly at T1, what is the start point, what is the end point, mark it there. If you keep marking it for different temperatures and join all the starting times and the ending times of the transformation, you will get this sort of curves. Okay, so this is TTT diagram, and this is quite useful to decide at isothermal exposures What is the time taken? Incubation period before this first C curve is incubation period. You can see at high temperatures it is a large incubation period due to low delta G bulk, and at low temperatures also it is large because of low diffusion, but at in between temperatures the incubation period is very low because the delta G is low enough, undercooling is low enough, therefore you get sufficient delta G for high nucleation rate, and diffusion also is not sluggish, therefore we get a very small incubation period. So this is how overall transformation kinetics is understood based on TTT diagram. Okay. So this is the procedure followed. Isothermal exposure studies are repeated at different temperatures. Fraction of product versus time plots are mapped to temperature versus time plot with the transformation start and the transformation end points. Okay. This is what has happened here, and by this we get this TTT diagram. A similar diagram may be important when continuous cooling is done. That's where CCT comes, continuous cooling transformation curves, rather than isothermal exposure. See, in isothermal exposure, we put the sample at one temperature and noted the start point and end point of transformation. Instead, if we go for continuous cooling from some high temperature to low temperature over a period of time, then the cooling rate curve is like this, that the start and end will slightly shift. We know the kinetics is going to be different when we cool it at a different, when we cool at some rate. Therefore, these are the starting time and temperatures. This is the transformation completion time and temperature. So these dotted lines are the CCT diagrams and the solid lines are TTT diagrams. So this is what has happened. Instead of isothermal exposure, continuous cooling is done and the transformation start and end point are mapped in temperature versus time plot. Okay, this is also quite useful diagram. Let's see how to simulate one of them, TTT diagram. There is an example in thermocalc P03 precipitation module 03, where iron chromium carbon alloy, which is having 12% of chromium and 0.1% of carbon, rest is iron. This alloy is high chromium steel, where 0.1% carbon is used. So this carbon with chromium in steels will form these phases, carbide phases. M7C3, M is metal, it can be chromium, and chromium 7C3 is one carbide, and M23C6, this is another type of carbide, Cr23C6 carbides. So these are prominent phases in this alloy. They form over this 500 to 800 degrees Celsius temperature range. So we'll make a TTT diagram which covers this entire temperature regime and see how the overall transformation kinetics is. Keep the other parameters with default values. Let's see how to do that. Precipitation demo should be used, but I am not going to use that. I am directly going for example files. Precipitation module and P03 FEC Cr TTT cementite M7C3 M23C6. For these different phases, we will see the TTT diagram. So click on that and open. Wait for a few seconds. Now it's done. You can click on this system definer. Okay. Two databases, FEdemo, MFEdemo, both are used. Three elements, FECRC are selected. I go to precipitation calculator and show you the setup. Carbon 0.1 mass percent, chromium 12 mass percent, and matrix phase is BCC. And in the precipitate, there are three different phases. Cementite is one phase, M23C6 is one phase, M7C3 is one phase. Okay, these two are carbides. Cementite will anyway form this iron carbide. These are the different phases that are going to appear in this alloy. If we take initially one BCC and see with respect to time, what is the start time for cementite formation, M23C6 formation and M7C3 formation, and that is going to be done in this temperature range. So it's a TTT diagram, therefore isothermal exposure data for all this temperature range 500 to 800 range will be collected and plotted as TTT diagram. Okay. And the time, maximum annealing time 1 e power 8 is given, that many seconds, and other settings you can keep them in default values. More importantly, these nucleation sites are grain boundaries. Okay, so perform TTT. Once the calculation is over, you can see in plot and run for these three different phases, the start time at different temperatures are given here. Cementite, this is M7C3 and this is M23C6 carbide. Okay. This is the TTT diagram. You can try out the CCT diagram example on your own and see how the things are. Thank you. I hope the lecture is useful. See you in the next class.